Alex, I'd like you to look at your formula sheet on the back page. And if you look at the time dilation equation, it says T equals T0 all over the square root of 1 minus V over C, all squared. And then there's one that has an L in it, and I also noticed there's a square root of 1 minus V over C, all squared. Then I noticed that there's one with an M in it, and there's also a square root of 1 minus V over C, all squared. We're going to start to abbreviate that in just a second, but let's begin today's lesson. Put your pencils down, look up. So this is a video by Dr. Brian Greene. He's one of the world's leading authorities on Einstein and special and general relativity. He does some really good explanatory videos as well.
When Einstein realized that time elapses more slowly for an object in motion compared to the rate at which it elapses for us here on a stationary clock, he didn't just make a qualitative statement. He made a quantitative statement. He wrote down a formula that tells us how much more slowly time will elapse on that moving object. And if you like equations, the slowdown formula is...
And who doesn't like equations?
1 over the square root of 1 minus v squared over c squared. V is the speed of the object. C is the speed of light. But if you don't really like formulae...
Who on earth would qualify for someone who doesn't like a good formula? I don't understand that.
Let me show you that equation in action just through some visual illustrations. So here is a stationary clock with us on Earth. Here's a clock on a spaceship. Now, if the ship is not moving, the two clocks tick off time at exactly the same rate. But now, let's give that spaceship some velocity. 1,000 miles per hour. You know, reasonably quick speed. Notice that the slowdown, while there, is just too small for us to see it. That's why we don't know about the slowdown at everyday speeds that we can achieve. But let's take this 1,000 miles an hour and kick it up to a much higher velocity. 100 million miles an hour, about 1/6 of the speed of light, fast enough to go around the entire Earth in a single second. There is a slowdown on that clock. If you look really close, you kind of squint, you can kind of see it, but still, even at this very high speed, difficult to see, not a big slowdown. So let's kick up the velocity of the ship even higher. Let's bring it to 600 million miles an hour. The speed of light is about 670 million miles an hour. Now, this speed, the slowdown of time becomes obvious, right? This clock is ticking up time much slower than our clock here on Earth. And just to see it even more starkly, let's bring that speed of the ship even higher. Let's put it at 668 million miles an hour, just below the speed of light. And look at how time is elapsing on the spaceship clock. Very slow compared to the rate at which time elapses on our ordinary clocks here on Earth. And this really illustrates quite wonderfully how we don't know about the slowdown in our bones intuitively because we never achieve speeds anywhere near the speed of light. But if routinely we did travel at speeds near the speed of light, this slowing of time would be obvious to us. This dramatic slowing of time near the speed of light would be intuitive. It would be in our bones.
So, why don't we notice special relativity in our everyday lives? Well, look at the time dilation equation. Let's write it out. It looks like this. T equals T0 all over the square root of 1 minus V over C all squared. By the way, do you need to memorize that? No, it's on your formula sheet. Do me a favor, though. Can you all circle this square root thing? That square root of 1 minus v over c all squared, Riley, has a special name. We call it the Lorentz factor because before Einstein showed how and why light will always give you the same speed, no matter what, Lorentz was a mathematician who had figured out, look, I can make the numbers match if we divide or multiply by the square root of 1 minus v over c all squared. I can't explain it, but at least I can. He had discovered that particular factor. So we call it the Lorentz factor, and it's often symbolized or abbreviated with the Greek letter gamma. Greek letter gamma looks kind of like a skinny fish doing a headstand. Okay? So that gamma is an abbrev for the square root of 1 minus v over c all squared. It's what determines how much time dilates by. It's the time dilation factor. And so if you're lazy, I qualify, you can write the time dilation equation as t equals t0 divided by that. And I think I gave you that version on your green sheet as well. Did I not, I think? I don't care if you write out the equation the full way, Diego, or if you want to use the abbreviated method. You'll get full credit for either. Oh, Aryan, how would I get the T0 by itself? The gamma? Yeah. Over? Okay. Number one, this next example asks this. How much will 1 hour of time dilate for the following situations? I'm going to draw a little line like this. Here's what we're going to do. We're going to quickly calculate time back on Earth for 1 hour divided by the square root of 1 minus whatever speed I'm giving you. Aryan, did I give you the speed as a percentage of the speed of light? So I'm going to have to divide by 3 times 10 to the 8th, all squared. We're going to do a whole bunch of calculations in a row and just see what happens. And I've written it out generically, so I'm hoping that we don't need to rewrite it every time, Alex. Here's what I'm actually hoping. Get out your calculators, all of you, please. Okay? And let's start actually in the bracket. Suppose you're walking. So right now I'm walking at about 2 meters per second. Time is moving slower for me than it is for you. By how much, I'd like to know. So I'm going to go in the brackets 2 divided by 3 scientific notation 8. And I'm going to hit equals. I put the 2 in for the speed. Do that on your calculator. Do you all have 6.66? Okay? Then what would we do if we move out? Squared. Hit your x squared button. We figured out the little bracket. Now, Emily, let's go 1 minus that. So 1 minus answer button. And something strange happens. The answer isn't 1. But it's so small, my calculator doesn't track that many sig figs. So, is it true that when I was walking around the classroom, time was moving slower for me? Yes, technically, but is it noticeable? You know what? 1 second or 1 hour is the same as 1 hour for a human walking. It's just not noticeable. Your good scientific calculators, Ruby, can't even track it. Okay, let's go faster. What about on a race car? Let's put a 70 in for the speed. So now I'm going to go on your calculator with me, 70 divided by 3 scientific notation 8. And you should have 2.3333 times 10 to negative 7. Okay? Is that okay, Sarah? Oh, and then squared. And hit equals. And I get 5.44 times 10 to negative 14. And if I go 1 minus that, oh, again, the time dilation is so small that my calculator can't even complete the calculation. So is it true that a race car driver experiences time more slowly? Yeah, but it's not something we plan for, have to take into account. Ooh, what about the SR-71 jet? That was the fastest jet ever created. It could go 1,000 meters per second. Let's try putting a 1,000 where the bracket is in for the blank. So it's going to be 1,000 divided by 3 times 10 to the 8th equals squared equals 1 minus that. Oh. So I thought for a while, Josh, as I was making this up, what else moves? You know what? You know what else moves fast? The Earth moves around the sun pretty fast, actually really fast. So I said, let's try putting 29,600. So 29,600 in divided by 3 times 10 to the 8th. And I got 9.86 repeating times 10 to negative 5. Hit my x squared button. Then I went 1 minus that. Ha-ha! I got an answer. Now what? Now I'm going to take the square root of that. And then I'm going to go 1 divided by that. That should tell me how much more time we experience on the Earth relative to the sun, because relative to the sun is at rest relative to us. And I got an answer. For every hour that goes by on the sun, 1.000000005 hours goes by on the Earth. How many zeros? 1, 2, 3, 4, 5, 6, 7, 8. So let's write that down. 1.8 zeros. Is that going to affect our everyday lives very much? So then I asked, what else moves fast? You know what? The sun, the solar system, is moving through the Milky Way galaxy. There's a big black hole at the center of our Milky Way galaxy called Sagittarius A star. That means for us, time is moving more slowly than for that black hole. So I said, why don't I try putting that in? 2.1 scientific notation button 5 divided by 3 scientific notation button 8 equals squared equals 1 minus answer button equals square root answer button equals, and then 1 divided by that. Okay. 6 zeros and a 245. 1.12345 6 zeros. Still nothing to write home about. Meh. So now, Alex, let's go way faster. UBC has a particle accelerator. Oh, wait, we got someone just coming in. So UBC has a particle accelerator. It's called Triumph. I'm hoping, I would love to do a Physics 12 field trip there. I've been there on a tour. When it's running, there is a room where the magnetic field is so strong, you have to turn off your phones before you go in. The magnetic field is so strong that paper clips stand up on their end. They don't lie flat. Oh, yeah. Yeah. So they can get protons up to 2.24 times 10 to the 8th meters per second. What's the speed of light? 3 times 10 to... It's getting close. Still a long ways shy, but okay. 2.24 scientific notation button 8 divided by 3 scientific notation button 8 squared 1 minus that, square root of that answer, 1 divided by that answer. Now we're getting a little more interesting. UBC, the researchers there, when they're doing their calculations, they actually have to take into account that time is moving more slowly for the protons. When they're doing things like radioactive decay and things like that, if they don't take into account time dilation, all their radioactive decay estimates will be totally garbage. So 1 hour for the proton ends up being 1.5 hours for the researchers. CERN is the largest particle accelerator on the planet. It's on the border of France and Switzerland. It's huge. It's this massive, I think it's about 3 kilometers across, circular particle accelerator where they get things going really fast. So at CERN, they can get muons to 2.96 times 10 to the 8th. Okay, 2.996 actually, times 10 to the 8th meters per second divided by 3 times 10 to the 8th meters per second. Equals, and I get 0.9986, and then the 6 repeats. Oh, squared. And then 1 minus that. And then the square root of that. And then 1 divided by that. 1 hour for the muons is 19.4 hours for the researchers. And that absolutely they would have to take into account when they're doing their research. I haven't updated this. When I made this list up about 5 years ago, this was the fastest we were getting things, but I think now we're actually getting things even faster. But Stanford, the University of Stanford, Stanford University in California, has a linear accelerator, not a circular one. It's called the SLAC, the Stanford Linear Accelerator, and it gets electrons up to 2.9979 times 10 to the 8th. Okay, 2.9979, scientific notation button 8, divided by 3, scientific notation button 8, squared. 1 minus that, square root of that, 1 divided by answer button. By the way, the reason I've been also doing this in steps, if you're finding doing it all at once, you're always getting the wrong answer on your calculator, you can always do it this way. Start in the bracket and just slowly work your way out using your answer button all the time. Emily, that totally works as well. I got, 26.7. So for 1 hour, if the electrons are moving for 1 of their hours, that's 26.7 hours that the researchers observe them. So when we try by the way, you can get answers for a human and a race car and an SR-71. If you're bored, you can try this. Google long number calculator, and you'll find an online calculator that carries 100 sig figs or so, and you will get an answer. But none of our scientific calculators just carry that many sig figs, and so they always just round off. Because we all know the answer is not 1. Your calculator is lying to you again, but so close to 1 that it doesn't make a difference. Okay. How would you like to see time dilation illustrated within 10 seconds? Of course you would. Put your pencils down, look up.
This video would be 10 seconds long if you watched it while your computer was whizzing past you at 87% the speed of light.
There. A 5-second video would be 10 seconds long if you watched it while the computer screen was whizzing past you at 86.6% of the speed of light, because time would be slowing down for your computer screen, and so you would see the video moving slower relative to you. Time would be moving slower. All right, we've talked about traveling through time. Let's look at 3 simple ways to travel through time and 3 complicated ways to travel through time. One of my favorite YouTube channels, if you're a nerd, a good one to look at is called Minute Physics. Puts out really, really good stuff. In fact, that last one we just saw was a Minute Physics video. So let's travel through time.
Time travel can be complicated and complicating, so let's ignore all the paradoxical stuff and talk about a few simple ways that you can time travel without leaving your home. First, do nothing. You're already traveling through time.
Yeah. 1 second just elapsed. Another second just elapsed. So by default, all of us are automatically traveling through time because we're embedded in it, which is kind of lame, but we should point that out, at least mention it.
I mean, here you are, 15 seconds into the future since the start of this video. Easy, right? The point is, we're all always traveling forwards through time. But that's boring time travel. What's interesting is time travel relative to other people. To do that, start walking, and you'll travel through time relative to someone standing still. We've known for over a century that time and space are really just two components of a single space-time, and the faster you move, the slower time will pass for you. If you take a walk around the block, you'll be 3 femtoseconds younger than your friend who stayed home.
He used a long number calculator to get that. Our calculators couldn't get an answer that small.
Except in order to walk around the block, you had to stand up. You're now further from the Earth, and so gravity is a tiny bit weaker for you, which means you're traveling through time relative to your friend who's sitting down. That's right, more gravity makes time slow down too. If you stand up for a minute, your feet will age 10 femtoseconds less than your head.
Every time you stand up, because your head is slightly further away from Earth's gravitational field, your head is experiencing time slightly slower than your feet.
On the other hand, GPS satellites high in orbit experience less of Earth's gravity and thus travel noticeably faster through time than we do, which is why their clocks are calibrated to run slow. But maybe you want to time travel more than a few femtoseconds.
Okay, so the 3 simple ways: do nothing, go for a walk, stand up, and you are traveling through time. Riley, you going to make it? That was a long blink. Challenge accepted.
Get ready for your head to start spinning. I mean, the universe. Because if the whole universe were spinning really fast, general relativity predicts there would be time loops all over the place. Moving along one of these loops, you'd always feel like you were moving forwards in time, but overall you'd loop around and travel back to a time and place in your own past. It's a little like how you can keep moving forwards on the Earth, but Earth's curvature brings you back to where you started. Unfortunately, our universe isn't spinning. Maybe it would be easier to build an infinitely long, super dense spinning cylinder, which would also curve space-time enough to create a time loop. The problem, of course, is how do you build something that's infinite in size? Maybe you could just make it really, really big? No. If you tried to squeeze this time machine into finite space, you'd need negative energy, something nobody knows how to create, to make it work. Otherwise, you'd end up with a black hole. Wait, but what if instead of a black hole, we built a wormhole? Wormholes are hypothetical but not physically impossible bridges through space-time, shortcuts that can instantaneously connect two different places and times in our universe. If you had a wormhole, you might be able to use it to travel into the past or the future. The problem is that no one knows how to build a wormhole, or once you've built it, how to keep it from collapsing. As Sean Carroll has eloquently written, keeping wormholes open requires a form of negative energies. Nobody knows how to make negative energies, although they occasionally slap the name exotic matter on the concept and pretend it might exist. Well, that's too bad, but as a consolation, welcome to the future. Almost 3 minutes have passed since the beginning of this video, and we now have personal jetpacks.
All right. Enough about time. Ella, there's something else strange that happens. I'm not going to prove this one mathematically. I did the time dilation equation with you. But it turns out, if an object is moving really fast relative to you, not only is time moving slower on that object, in other words, if it was a glass spaceship and you had Superman eyes, you would see the people moving in what appeared to you slow motion. Not only is time shorter, lengths are contracted in the direction of travel. Distances change. So, Einstein's special theory of relativity says this: the length of an object will be measured to be shorter when it's moving than when it's at rest, but this shortening is only seen in the direction of travel, in the direction of its motion. And there's an equation for that too. Next page. This is also on your green sheet. I'm going to use L for length because I think that makes sense. Okay? If the length of an object when it's standing still is L0, the theory of relativity predicts that the object's length L when it's moving, speed v, will be measured to be L equals L0 square root of 1 minus v over c all squared. Although it's sometimes written as L equals L0 times that abbrev. I'm going to use that abbrev because it's less writing, and I'm a nerd, and it lets me use a Greek letter. To me, that's like a triple win. Okay. I think you already know what v is, how fast the object is traveling. Diego, I think you already know what c is, the speed of. Yep. So what we're going to need to memorize is what L and L0 is. Unfortunately, it's not quite the same as T and T0. L is the moving, or in fancy terms, relativistic length. T0 was time on the moving spaceship. L0 is not the length of the moving spaceship. L0 is the original length at speed 0, at rest. So I've given you two ways to remember what L0 is. You can think of it as LO, original length, or you can think of it as L0, the length at rest. If you're at rest, what's your speed exactly as a number? 0. So, let's suppose we sent a meter stick, this very meter stick that you see, whizzing past you in this direction at, how fast? 99.5% of the speed of light. And let's assume you all have Superman eyes and can see something moving that fast with a great deal of accuracy. How long would the meter stick be as far as you were concerned? Okay, good question. So Alex, example 1 says, how long would a meter stick appear to be if it was moving past you with a speed of 99.5% of the speed of light? Alex, what's this question asking me to find? How what? Long. So L or L0? And that's the tricky part for this. Sorry, but this is the stuff you will have to memorize. Is it asking us to find the relativistic moving length yes. This is asking us to find L. Did they give me V, Alex? How would I write that as a decimal in our notation here? 0.995 C, don't forget the C. That must mean, now Alex, we're going to see how clever you are. It's a meter stick. How long is a meter stick when it's at rest? Thank you. I've had some classes that couldn't come up with, they didn't tell us it's a meter stick. Okay. Let's write down our length contraction equation, and lengths contract, they get shorter. It's going to be L equals L0 times the square root of blah, 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 blah. So let's plug in our numbers. 1 times the square root of 1 minus 0.995 C over C all squared. Alex, do you see? Do you see? Do you see? What do you see? That's convenient. Probably the 1 times in front isn't going to make a difference, but go to your calculator. What do you get? And all of you, again, want to practice typing these in, because if you can't type these in, you're out of luck. Let's see. Square root of bracket 1 minus 0.995 squared. Do you get 0.099? You know what? If I round that off, I think you get 0.1 meters. So the meter stick, Sadie, as it went zipping past you, would look exactly that long. All the letters would be shrunken in this direction, so all the writing would look really skinny and tall. The height wouldn't change. It would still keep the same thickness as this meter stick, but it would be that long. Oh, and here's the weird thing. Let's suppose you had a little tunnel that was half a meter long, that was this long. While it was moving past you at the speed of light, at 99.5% of the speed of light, it would fit inside that tunnel. As soon as it came to rest, it would no longer fit inside that tunnel. I told you something like weird but cool. I hope I used that phrase. Yes? This is our universe. Example 2. Yeah.
So like if it was slowing down slowly, would it like slowly grow?
You would see its length consistently changing and getting longer in the direction that it was slowing down. You notice I'm picking my words very carefully here. I have to. Okay? Yeah. We're going to start to dive into that meter stick tunnel paradox and ask, okay, what would happen? Because there's some weird stuff that's going to happen here. Anyways, I like example 1, I like example 1, I like example 2, I like example 2, I like example 2. An 85 meter long spaceship passes you at 2.23 times 10 to the 8th meters per second. How long does the spaceship look to you? I think that 85 is when it was at rest, because it's asking how long it looks to us. The spaceship is moving. I think it's asking us to figure out the relativistic length. I think this is asking us to find L. I think the original length at rest was 85. V is 2.23 times 10 to the 8th. Alex, this time, unfortunately, I won't be able to use that. Do you see? I'll have to put the 3 times 10 to the 8th into the equation because it's not going to cancel this time, but okay, I can do that. Again, here's our length contraction equation. L equals L0 times that gamma function. It's going to be 85 times the square root of 1 minus 2.23 times 10 to the 8th all over 3 times 10 to the 8th squared. This is about as complicated as you'll be asked to type, so see if you can type this into your calculator. I'll do it up here. Those of you that have the fancy schmancy fraction buttons can take some shortcuts, but Diego, you and I, no, you have actually, I think, you might even have a fraction button on yours, by the way, because you have a square root indent button. Casey, who has a TI, we have to go 85 times square root bracket. I know, by the way, if I don't put times, just put the square root, it assumes it's times, so I can get it without hitting times. 1 minus, open up another mini bracket, 2.23, scientific notation button 8, divided by 3, scientific notation button 8. Close off the mini bracket, squared, close off the square root. And if you've typed it in right, you'll get 56.9 if I round off properly. So the 85 meter long spaceship would look 56.9 meters long to us. We would see it kind of stubby and tall. Now, the people on the spaceship won't notice anything because how fast are they moving relative to the spaceship? 0. So for them, the spaceship will be 85 meters long. When they walk along the spaceship with a tape measure, it will be 85 meters long. But to us, in our universe, relative to our reference frame, it will seem short. Oh. What if you went zipping by the Earth really, really fast in a spaceship? you would seem really, really short to the people on the Earth, but wait a minute, as far as you're concerned, you're at rest, and it's the Earth that's zipping past you. Here's what you would see. The faster you went, the more you would see Earth looking like that. And if you went at like 99% of the speed of light, the Earth would look like that to you. That's the universe that we live in. By the way, that means while you were moving at that speed, any experiment that you tried to do about the Earth would tell you that its width was that. That's why when we did that star trip, when the people actually measured the distance in light years, they got a different answer because space-time itself was contracting in the direction of their travel. Example 3. I added a part A and a part B. I should have included it in your notes. You can just write it as we go, but read along with me. It says this. Suppose a spaceship is 100 meters long when stationary. You know what? That must mean L0. It's the original length at rest. When it moves past an observer, the observer measures the spaceship to be 25 meters long. Ella, that must be plain old L. How fast is the spaceship moving relative to the observer? Sarah, what's this question asking me to find? Look on your green sheet near the bottom. There is a V equals equation that has L's in it. Sarah, can you read me the V equals equation that has L's in it? Square root. L over L0, L squared. Okay, and for part A, I want the answer as a percentage of the speed of light. To do that, Sarah, I'm just going to leave the C as a C. But I'm going to evaluate the actual square root. 1 minus 25 over 100, all squared. There's a bit of a built-in error check here, Sarah. If you get L and L0 mixed up, if you put the 100 on top, if you try going the square root of 1 minus 100 divided by 25 all squared, you're going to get an error. If you're doing any of the special relativity stuff and you get an error, you probably accidentally mixed up your 0 and your non-zero term, your T0 and your T, or your L0 and your L. So there's a bit of a built-in error check. Anyways, it's going to be the square root of 1 minus bracket 25 divided by 100, close bracket, all squared, close bracket. I get 0.9682. So 0.9682 C. What percent of the speed of light is that? .9682. First of all, if you said 96, I would glare at you and I would say, well, it's at least 97. Let's go to 4 sig figs. Yeah, it's 96.82% of the speed of light. What if they want an answer? Did that work okay? Yeah? Okay. What if they wanted this in meters per second? How would I convert this number here to meters per second? Well, actually multiply it by C. What's C as a number? So just go answer button times 3 times 10 to the 8th. If they want it in meters per second, this is 2.905 times 10 to the 8th meters per second. Mr. Duick, how much should we round off to? On a test or a quiz, I'll probably tell you, but usually for relativity, I tend to go to 3 or 4 sig figs. I like example 4, I like example 4, I like example 4. Example 4 is a nice question. And we'll finish off with this question. Then we'll press pause. A certain star is 15.6 light years away. How long would it take a spaceship traveling at 95% of the speed of light to reach the star? A, relative to the people on Earth. B, relative to the people on the spaceship. And C, what is the distance that the spaceship actually travels? I'll give you a hint. Not 15.6 light years. All right. Riley, what does A want me to find? And by the way, this one is worded badly on purpose. So if you're finding this tricky, you're normal. Start with the word how.
Oh, how long did it take to measure fire?
So is it asking me to find a length or a time? How long would it take a spaceship to reach the star? Is that in English? Because I've told you, how long is a vague phrase. I did that on purpose. Is that a length or a time? What do you... Sorry? Time, I agree. Time 0 on board the spaceship or T back on Earth? Okay. Have they given me time 0 on board the spaceship? Be obvious, Riley. Read. Have they given me time 0 on board the spaceship? Where? Is 15.6 light years? Is that time? No. That's a distance. Is 0.95 c? Is that time? Did they give me T0? Be obvious. Say no. No. Okay, and that's important for this specific question. That tells me, they didn't give me time 0. I'm not using relativity yet. I'm going to use d equals vt plus a half at squared. But what did we say a was for this whole unit? 0, because Einstein didn't know how to deal with acceleration. Okay? So your hint for part A that it's not special relativity, it's not time dilation. They didn't give me time 0. How would I get the t by itself?
5v.
So t is d over v. What's d? 15.6 light years. What's v? 0.95 c. Oh, Riley, do you see? Do you see? Do you see? What do you see? And notice the only units left behind are years. I am getting time as an answer, which tells me I probably set this up right. So, as far as we're concerned, it's going to take the spaceship 15.6 divided by 0.95. 16.42, I'll go 16.4 and I'll store this on my calculator. Years to get there. Sadie, will that be how long the people on the spaceship experience? No. Sadie, what's B asking me to find? As measured by observers on the... So that's going to be, is that T or T0, folks? Time on board. Okay, now we're into relativity land. So that must mean, Sadie, they gave me a speed. Did they give me a speed in the question? Oh yeah, 0.95 c. Yes? And that must mean, Riley, I must know T. That's why I had to do A first. I'm going to write 16.4, but Riley, you know I'm using my answer button instead, because it's 16.421052. I'll use my answer button. Sadie, can you find the time dilation equation on your green sheet, please? Or on Riley's green sheet, because you fool if you don't have yours. Oh. Let her find it. Let her find it. This is how we learn. So it's the one with the T's and the T0s in it. Yep. Now, you see, I think it's T equals T0 over some square root thingy. Is that right? We want to get the T0 by itself. What's that square root thingy doing to the T0? Oh, by the way, before you got here, we called that the gamma function. It's actually an abbreviation. So now I can say, what's the gamma function doing to the T0? Adding, subtracting, multiplying, or dividing. It's on the bottom, so how will I move it over to the other side? So here it is. Our time zero equation is t times the square root of 1 minus, and before you got here, Sadie, we said we abbreviate that square root of 1 minus v over c all squared with that, because we get tired of writing it out. We're naturally lazy. So Riley, I'm going to write 16.4, but I'm going to use my answer button. Square root of 1 minus, in brackets, 0.95c over c all squared. Hey folks, do you see? Do you see? Do you see? What do you see? Conveniently, the c's cancel. That's always nice when that does happen. So we're going to get out our calculators. Don't type 16.4, Casey. Hit your answer button. And then times square root bracket 1 minus 0.95 squared, close bracket. 16.4 years will go by for us on the Earth. 5.13 years will go by for the people on the spaceship. Okay, cool. Finley, what's C want me to find? There's two ways that we can do this. There's two ways that we can do this. The first way is to go, well, distance equals speed times time. But since it's the distance that the spaceship is moving, it's going to be speed times time zero. Finley, what's the speed? 0.95c. What's the time on board the spaceship? I'm going to write 5.13, but I'm going to use my answer button. Also notice, Finley, in my units, I get light years. That is a distance. So if I go 0.95 times answer button, even though the Earth measured the distance to be 15.6 light years, the distance the spaceship will travel, because the length of space itself is contracting in the direction that they're traveling, is 4.87 light years. There's another way I could have done this. I could have used the length contraction equation. Can you read to me, Finley, the L equation, the length contraction equation?
L equals L0, square root 1 minus v over c squared.
L is the relativistic length. L0 is the original length. If we go L, what was the original length measured from Earth in light years?
15.6.
Times the square root of 1 minus 0.95c over c, all squared. So I got 14.87109843, using my answer button all the way through. Casey, if I use the length contraction equation, where's my typo? One extra bracket. I also get 4.871098. The same answer. And first of all, what this does is this confirms that this equation is correct, because I didn't prove it with you, but it gives us an explanation. The reason the astronauts measure the distance to be shorter is because, as far as they're concerned, they're not moving. Space is moving past them, and so it's contracted. So, what does this mean for objects that travel at the speed of light, like a photon? You know what? Let's go L equals L0, the square root of 1 minus, but let's put the speed of light in for V. Aryan, what's 5 divided by 5? What's 10 divided by 10? What's anything divided by itself? So what's C divided by C? What's 1 squared? 1 times 1. What's 1 minus 1? What's the square root of 0? So I told you the other day that photons don't experience light. I told you that time. I told you light was special. Photons also don't experience distance. So I've turned on again my flashlight. As far as you're concerned, in your reference frame, Sarah, the photons are traveling from my phone to your eyes. As far as the photons are concerned, they're everywhere in the universe at once. Ella, you may have looked up late at night at the stars and marveled to yourself, wow, the light from those stars had to travel tens of light years or hundreds of light years or thousands of light years to reach my eyes. Wow, only relative to you. As far as the photons are concerned, they traveled no distance at all. They left the star, they arrived in your eyes, and they did not travel the distance in between. Because distance means nothing for a photon. Or, as I like to say, light is special. It's really cool. I'll show you the video about black holes and time travel next class. I want to give you at least some time to work on the take-home quiz. So we're going to pause here. We'll pick up with this on Monday. So your homework for Monday, you want to get the take-home quiz done for sure. You got Flex, you can work on it a bit too. And technically the time dilation homework from lesson 3 is due Monday.